Afternoon, good evening, gentlemen and ladies. We're going to start this session today. This was supposed to be anchored by Akshay Malviya, but he has been suddenly had COVID and had to pull off. So I will do the anchoring as well. And before we start, I just want to mention that the proceedings of this session will be recorded, and we shall present this over YouTube later on. So all these proceedings will be in the public domain. So all participants are requested to take responsibility of statements and expressions which may affect themselves on the public domain, and make statements with care to remain compliant to those rules and not to create a breach of any copyright and other elements if they are referring to items in their statements. So we'll go quickly. I have been working in Australia for some time now, having been CST on the Indian Railways before I took voluntary retirement and moved to Australia. And it is engaged in basically in the design, various designs in Australia, though for short periods I've also done stints in the management as a project engineer, as a managing director. I am also the competency manager and a manager of the licensing agency for IRSC. So I've been presently engaged for a while on advanced signaling projects, and one of the aspects which I shall and will discuss in this session is about the designing of the trackside fit for advanced signaling. Just to be sure, if I may ask any one of you to please confirm that you can hear me right. Can you confirm, Seshadri, I can see you?
Yes, Somat, we can hear you.
Okay. Thank you very much. Just to be sure that we are not. And you can see also the slides, right?
Yes, yes.
Thank you. All right. So I shall also, today we have with us Mr. Seshadri Belur, who has been here also in Australia. He will be presenting an interesting subject on the management and control of level crossing gates as they do here in Australia. And he has been a Bachelor of Science before he joined the Indian Railways, and he is professionally a fellow of the IRSC. He is a fellow of the Engineers Australia. He's a member of IRSC, sorry, and a fellow of the Engineers Australia. He is an APC engineer. He is a member of the IEA Australia, and also he is a member of NER. He's a trained lead auditor for the ISO 9000 quality, and he is a Microsoft certified professional. He joined the Indian Railways as a signaling engineer in 1980, and then has a 42 experience in design, verification, installation, and testing of railway signaling installations and train control system design, check, verify, and construct, test, and commissioning of railway signaling installations. So he also is experienced in data and accel counter system design. He does drafting and verification of designs, and he he has a quality. He also sorry, I just yeah, drafting and verification of design and quality of documentation related to organizations, companies, to signaling installations. He worked in various capacities as a signaling design and maintenance expert, an assistant divisional signal and telecommunication engineer on the Indian Railways, that is in Western Railway. He was awarded the General Manager's Award in 1986 for commissioning the pilot project for the installation of AWS system over Mumbai Suburban Railway, and has a strong background in design, verification, and factory acceptance testing of signaling installation. And now supports design and teams in delivering projects in the timeline set by the ARO in Australia. So having done the introduction of ourselves today, we shall go over to the presentations, and as I mentioned before, I shall do the first presentation, and welcome you all again for attending this session. So I will now start with the presentation that I have planned for the day, which is basically a presentation on the signaling for on the trackside, the design of the trackside systems for advanced signaling. So this is the subject, advanced signaling trackside design, and what I intend to discuss in this session is the way the trackside is made fit for advanced signaling. Mainly, I will be talking about the way the ETCS signaling is done, and I will be talking of how the ballast system is provided on this and in this session, I will be referring to generally the ETCS standards, as I had mentioned. I would request my or those in the audience, and when required, to refer to basically the two subsets 0 to 6 and the 040. I've given the links to them, and when you are free to go through them, it would make an interesting reading, and most of the elements that I have discussed in this session is based on the same, on these two standards. So yeah, so from here we go on to the subject matter of this session. So before we go ahead, I want to first give a quick description of the operating environment of the trains in an advanced signaling system. So this is a very simplified description of the environment. This is the track, obviously, and I am showed a train here. Now we have an element where we have the interlocking system. A part is presently, obviously, this is a software controlled processor based equipment, and we all have a radio block center which transmits the information of the availability of the track for movement of a train through a radio link. So the main medium of conveying that the track is free to travel to the train is via radio link, which is done to the ETCS standards using GSMR's radio system, and to ensure that the train is provided with the distance information which is safe, there is a need of a reference. The reference generally, or what is chosen is the ballast, but the ballast is obviously as we shall see, the ballast is the last reference ballast group which is used as a reference for the distance by the train. So, in the picture above, we show that a train is running between two ends, and this train, when it has passed over the ballast, has registered itself as a train over this ballast to the RBC, and then the train is provided with an information from the RBC over a radio link here, telling how far it is from the point of conflict or the point up to which it is allowed to run. In this case, if it is allowed to run up to this point, then it will be given an information about the distance that is existing between the front end of the train and this point, which it then moves. However, we shall see that this information needs to be controlled in a manner so that there is no loss of safety and there is no hazard. So how is this taken care of? Now, one of the most important part of this is obviously the way the vehicle is localized. That is, when you look at this slide, that the vehicle is located, that the vehicle is placed in front of the this ballast, which is called the last reference ballast, as I said. The RBC, the radio block center, uses various algorithms, and this is called the localization. So the train is localized in front of the ballast, and this forms the basis of a lot of things which happens when we run the trains in this system. So the ballast is used to localize the train. That localizing means that it is used to ensure to define within the system. The RBC defines the position of the train, and this is the localization of the train. Now, the ballast is the point which is used to create this image of the train in the system, in the RBC, of its position. Now, the ballast itself is powered by the train as it comes over it, and it is such that when the train comes within 1.3 meters of the ballast starts communicating with the onboard system. Now, the onboard system then transfers this information to the RBC and also obviously takes a part of it. And the main thing is the onboard system, when it transfers the information of the ballast to the RBC, creates the image of the train in the RBC of its position. Now, as the train moves forward from the ballast, as the train moves forward from the ballast, the distance of the train from the ballast is updated in the system, and thereby its distance to travel before its hazard can be calculated by the system, the RBC and the onboard together, and it ensures that the train will not exceed what is known as the end of authority, the point up to which the train can travel without hazard. We shall see this further when we proceed further in this discussion. Now, in addition to the positioning of the vehicle by the use of ballast, we also have some fixed localization using some form of traditional trackside, for instance. This is needed not for the system per se, but will be needed when there is a requirement to recover the train. So these sections, these fixed sections which are available, this information is available to the IX, the interlocking, the IXL, and thereby even if there are reasons which cause the localization information to be lost, the train will not be lost to the system and it can be recovered. However, we shall not discuss about that aspect today. Now, we shall then go forward to the next part and to the seeing how the movement authority is created. The movement authority is the authority given to a train to go to this point up to the point of hazard by the RBC. So it is entirely carried over as a radio message, and it goes and allows the train to know how far it can travel. Now, a part of the interlocking system, the interlocking system also is used. We are talking where the position of the train as available to the IXL by traditional means and by the train control system information, it sets and it allows the trains to use a route. So the IXLs, as in almost in a conventional, like a conventional interlocking system, performs checks to identify the routes over which the trains can travel. However, it completes the route and makes it available to the train, books it, locks it for the train, and then transfers the information to the RBC, telling the RBC that now look, there is a route available for the train which, if localized in the section, can be allowed to move based on its operating needs. So now the RBC gets the information about the position of the train based on the LRBG, and then it also finds out how far it can go, and this information is made available to the train, which then moves and continues to monitor the distance it has traveled to determine if it is still safe to move or otherwise. Where it comes near to the end of the authority, it then starts to slow down, which we shall see shortly. So there are various we shall just now say now for the train to move, some logical operating environment is created in the system, the RBC and the train on board together, which consists of the following elements: a end of authority, a danger point, and a supervised location. So to understand this, we can refer to this figure. Now consider this train which has passed this LRBG, and when this LRBG has been passed, the RBC, by virtue of its communication from the onboard, is aware of the train has passed this LRBG, and then it knows from the IXL how much route has been set aside for this train, and provides a movement authority to the train, which basically tells the train to which point that is it can move safely, and that is actually the end of authority, though the up to but the front end of the train can actually go up to the what is called the danger point. So you have one which is called a danger point, you have the end of authority, which is basically an element of the route which is available, and there is the element, another element which I have not discussed so far, which is the limit of authority, which is basically a point where the train may be need to run at a slow speed and come like a stopping point, for instance, for operational reasons. And then it from there onwards, it will not be stopped by the system because the danger point is still ahead, but it can be defined a lower speed so that a train can be stopped most efficiently. So as the train moves, there is a monitoring of the speed of the train to the follow a curve which will ensure that the train doesn't come to a stop, or rather slows down unnecessarily, or before it's needed to be. Similarly, not to go faster than it's needed to be. Now, in addition to these 3 points, we can also have an overlap, which is a point which is created by what is known as the supervised location, up to which the train may travel under certain conditions, but will never be breached beyond at all. However, it is not the train will actually trip at the danger point. So only advantage in giving a SVL is that the train can approach the end of authority at a higher release speed, thus improving the running of the train. However, the no train, so the distance is basically the overlap made available for improving the release speed and improving the running. Now, one of the main thing that we must consider is that as the train travels from the ballast, it it calculates its position by using what is known as the odometer. Now, the odometer in the train on board odometer has an error. Now, the position of the train, the exact position of the train will always be affected by the error in the odometer, and it has to be ensured that the train does not exceed the danger point or the end of authority, as we have just seen. Now, the if however we if however we not if however the corrections due to the odometer is not taking place, then obviously it can go ahead of the end danger point. Therefore, what the train does is it has a value, known value of the maximum error. So the train will ensure that it moves in a manner so that it is never in front of the point of conflict, that is the danger point, and for that it will try to move the train, as I show here, in rear of the danger point by a distance equal to the maximum error that can happen due to the odometer. So if you consider that there is only one ballast, for instance, in the whole system, then this, as the train moves, the error in the odometer will become larger and larger, and there will be need to bring the train to a stop, much not to a stop, or reduce the train to the release speed at a point which is much earlier or much in rear of the danger point. Therefore, there is a need to add more ballast so that the train can have a valleys nearer to the danger point, and it can move further closer to the danger point without the fear of its overshooting it under any circumstances, because the odometer error accumulates based on the distance from the LRBD. So therefore, in a in a system, in an actual system, you will have several valleys placed to, to ensure this. So now we shall now see what are the this how the safety and distance of the ballast matters. Now, if we, as I said, if we have it very far from the endpoint, we are going to have an error which is very large. And if the ballast is very far away, then you have to stop, you have to reduce the speed much earlier in rear of the danger point. Thus, effectively, you will have a reduced capacity in actual terms. So, if you consider that the trains will not stop, you don't have any stopping point at all, then you can assume that the ballast can be placed, only one ballast will do, because you are not stopping the train, but that's not the case. So you will have stopping points, and now the limitations or the placement of the ballast becomes important. Now, even if you have a stopping point, if you are not regularly stopping a train and you have created the stopping point only in case a train is not able to clear the section in advance for capacity reasons, then the accuracy of stopping the train is not high. And because the accuracy is not high, then the ballast can be kept uh, much much in rear of the train. Whereas if you are if you have a ballast nearer to the end of authority, you will have much lesser error, and so you can place the ballast. You need to place the ballast nearer to the point of error. So now we shall quickly see the. So please refer to this slide. Now consider this the ballast and the train and its endpoint. Now, if the ballast, if the train stops at this end of authority, commonly like where you have a platform stop, or where you know trains will stop very frequently, you will have a ballast which is very close to the end of authority, but at the same time the train will necessarily cross that ballast most of the time, will cross the ballast when it comes near to the end of authority. So it will probably be some 58 to 100 meters or somewhat, but the exact values will actually be advised by the design teams who considers all the factors and will advise the exact location of the ballast, but it will be very close, maybe a few hundred or even not few hundred, but about 50 to 100 meter maybe. And this ballast then will be that close to it. However, where the train is not coming to a stop very frequently, then this same ballast you can be placed almost some few hundred meters away, and this way the train will still be able to perform without any problem, because trains will not be generally expected to come to a stop here, and it is expected that the ballast placed at this distance gives the best operating performance. So you have to therefore be advised by the modeling and the basic design team, who will advise you on the placement of the ballast based on the type of stopping point, that is whether they are likely to be used more frequently or it is to be used very little. There is also a factor that if some stopping points you may need to stop the train more accurately, like if a train stops and it is likely that it will block the next section if it is slightly wrong, then also you will need a ballast nearer to the point of stopping. So for running of the train, you have to be told about the best place of the placing of the ballast from the stopping points, and that will be then used in the design. Now, this is in addition to such ballasts, you also need ballasts for the purpose of uh, resetting. For instance, you consider that a train is moving and it takes a diversion. Now, when it takes a diversion and it comes out and converges onto the main line again, the the distance, the LRBG information needs to be reset, because then for the section where from where it converges. So you will necessarily need ballast in front of in advance of the trailing points, so that the train which comes out of a divergence is able to reset its odometer, recalibrate, and then restart the distance calculation, and its error controlled thereafter. So from so we see therefore that we need the ballast for ensuring that the trains can run efficiently with stopping points. If there are no stopping point, one be fine, but obviously that's not a practical scenario. You have stopping points, so you start putting ballasts in the rear of every stopping point, and depending on the type of the stopping point, we place the ballast either close to the stopping point or slightly further ahead, further in rear. So that would definitely be determined by the best performance of the trains for running in the section. And then we know that we place ballast for resetting the meter, like where you have a divergence, where you have a discontinuity. So there you will need a ballast to reset the distance measurement by the odometer. Now, other than these ballasts, we also need a ballast for special cases. Okay, so special areas. Sorry, I should first mention about the ballasts other than the ones that I just described, which are mainly needed for running. There are also ballasts which demarcate the boundaries for special areas, while you are approaching special areas or you are in the special areas. So, for ballasts of this kind are those where, like in the border areas. Now, where you have a border, that is a border between the border between two levels. Consider that this is a case. Now, this is a case where we have a L0 in this section and we have L2, level 2 in this area, and this is the border. Now, here the train it has to move from L0 to L2. Now, when a train is moving from L0 to L2, for instance, we need certain mechanisms to prepare the system to take this train in. Now, when it comes and is needed to cross the border, the route inside the next area should be set in time for the train to come in. It should not be done too early, nor should it be done too late for the best performance. Obviously, that is the ideal. Now, to ensure that it is necessary that we detect the train when it is sufficiently in advance to prepare this area to pass the train at the right time without blocking the L2 area for unnecessarily long time. So how do we do? We need to place certain balances in rear of the approaching train to the border. So we have balances which first starts the radio, first creates the link to the radio system, then it establishes it in well in time. So by the time the train comes to the breaking point, so let us assume that this is the place where the train would have to be would be at a breaking distance from the border. So if the train is not allowed to go through, then obviously it has to start breaking from this point. But that is not the desired case. The desired case is where it is such that the train can move to the border and cross at full speed, and therefore at the point where when it comes here, and if the border is ready to take the train into the L2 area, the timing of these or placement of these balances are such that if the train was already fit or has a free access to the L2 area, this signal should be green, and then it can travel, and this is established by the this is not established, this is held by these balances which take care of all the processes in the RBC to exactly ensure this, and then it goes into the other area. Similarly, when it is coming out also, the same feature is required, and then it takes care of the train to go into the other side. Now, this is a case of this is the case of balances being placed to improve the performance, but but in a special area where the train is not in the L2 area, for instance, here. There are also the reason to manage the case where a train is the advised of its exact position, like as it the borders. Now we have already seen, for instance, here there is another this valley is it's at the border. Now this when the train comes at this location at this valleys, it means that the train is now accurately located right at the border, and then this is a case where the balance is ensuring the safety, and that this balance will not be required to be passed unless there is an authority here. So there are similar many other types of balances which stops trains from moving past the authority. So here is this here we have the generalized scenario where there is an end of authority which cannot be crossed by a train unless it is in the correct mode and has the correct authority. Now, in such cases, the balance is placed very close to that point, say within 3 meters, and it is such that the no train, the balance, the antenna of the train, the antenna of which picks up the balance information will not be crossing this point unless the authority is there, because if it crosses, the train will trip. So this is another class of ballast which we have to cater for, and typically is, as we have shown, is in the border. It can also be in the case of a train which is in the which is at the limits of the shunting, that is as you, so that once you enter a shunting area, for instance, you won't be allowed to it unless you have the authority. You cannot come into the main line at these shunting areas. If you are in a mode which is not allowed in the main line, then the train will remain within the shunting area and protect not with these balances acting as the guard. Now, there is also, say, another case is where a train has a mode which is not suitable for going past a particular authority, living on in authority. Then also we can have balances. Like a train may not be allowed to go past a authority, the end of authority, in the staff responsible mode. When it is like that, then we also place ballast, which is known, which will ensure that if the mode is not matching, the train will not go past that end of authority. So I've given a quick review of how these ballasts work and how they help run the train and maintain safety. So I would, as I said in the beginning, please refer to the subset 0 to 6, which is very useful in this for this purpose, and which gives the details of the way the ballast and this interacts with and creates the system, the environment of the ETCS. And with this, I will end my presentation from my side and throw open myself to answer any questions you may have in this subject. Yes, please. If you have any questions, please feel free to ask me.
Sir, what is the optimum distance between two balances when they are providing it?
Yeah, I believe, though I think okay, there is a maximum distance which you will be advised. It actually should depend on the kind of operating environment that you have. Probably it is around 2 kilometers or so, because that is the maximum which you may be able to run without causing a problem. Okay, but maybe Vijay is there. Vijay may be able to give a clear, better answer, because we go by the guidances that we get in the matter, and how they arrive at that guidance, I am not privy to that. So maybe Vijay, we can know if how they arrive at it. I believe they would have arrived at it based on the kind of traffic and other advice. But there is a figure that you will have to work to, and it's probably around a couple of kilometers. That's not the optimum. It is the maximum. Okay. The optimum distances, if you say, it will vary depending on the use. Like as I said, if you have a location where trains are stopping frequently, you will have one optimum distance that is probably within less than 100 meters. But if you have a case where the stopping point, if the trains are not stopping very often, the distance will be a few hundred meters or so. All right. So, but this is specific to the project that I know of. It may be different in others.
Thanks.
Okay.
Good evening.
Yes.
Yeah, just a very quick question. If I want to increase the number of trains per hour in the section, should I go with the consideration that I should increase the number of balances?
It has to be, because in the sense that if you have more trains, you will have more stopping points catered for, and therefore you will have more balances. But there is one point I would like to mention is it should all be advised through a more kind of simulation and modeling, because if you ask me theoretically, you can always calculate, you can always take trains from the same LRBG, correct? So, but you will have, you will lose the accuracy of stopping, and so for every stopping point, you should be having some point of some type of BGs.
So then can we go with the reference that more balances mean less speed for the train?
No, it should actually increase.
Okay.
The average speed should increase because your accuracy, if you have more balances, your accuracy will be increasing. Obviously, you have to put it with a proper simulation so that you put it in the right place. In engineering, obviously, we try to ensure that we use the minimum number of ballasts to achieve the maximum efficiency, right?
Yeah, correct. Okay, so increase the number of will mean that there will be some conflict with the efficiency of the train.
No, why should it happen?
Because you are going to now control and monitor the train more accurately.
The BG does not control it. The BG only helps it to run. If you have only one BG, for instance, you can run, you can take a train only so close to another to an obstruction, depending on the distance it is from that BG, correct? So theoretically, I don't know. I mean, I don't believe that there is such a system done actually, but you can run the train and then you add the error and then you put the train behind by so many meters. So therefore, because you are using one BG, you will lose for every train, you lose the amount of capacity equivalent to its distance from that ballast. So as you give more ballast, it will be losing less and less per train. Correct?
All right. Okay. Thank you.
So that way, if you have more ballast, you should look, generally with every stopping point, we give one ballast at least. Okay. That is the simple practical thing which happens. Now,
okay, right.
Yeah. Okay. All right. If there are no more questions, Sadri, will you take over and then you can move on to your presentation?
Yeah. I'll share my screen. Yeah. Yeah. Can you see my screen? Yeah, these slides.
Yes.
Yeah.
Yeah. Okay. So good evening, gents. Today I'll be speaking about the level crossing working in Australia and in particular level crossing working in Victoria. The subject is too vast, but I will try to cover as much as possible because the time constraint is there. So let me start with the introduction. What is a level crossing? So in simple and layman terms, any path or road that crosses a railway at the same level is called as a level crossing. And in general perception, when we say level crossing, it means level crossing which is having boom barriers, flashing lights, and belts. However, the actual classification is something different. And as per the Rail Safety National Law of Australia, level crossing is an area where a road or footpath, pedestrian or bicycle path crosses a railway at substantially the same level, whether or not it's signed as a level crossing. Okay, and as per Rail Safe, level crossings are high risk areas where rail traffic crosses the paths of road and pedestrian traffic at the same level. A major risk to rail safety by exposing train drivers, passengers and pedestrians, motorists and cyclists to collisions that often result in serious injuries or fatalities as well as financial costs. This is as per ONRSR policy. Now, why do you say that the high risk level crossings are high risk areas? Some of the reasons are level crossings are physically interfaces between road and rail traffic. That's why they are high risk. Both modes of transport are operated by entirely separate entities and have different rules, procedures, and characteristics and operational limitations. Most importantly, though, neither has the advanced knowledge of how the other one is operating. And in Victoria, the road traffic is managed by Vic Roads, whereas the rail is managed by rail infrastructure managers like V-Line, MTM or ARTC. And both of them, Vic Roads will not be knowing how V-Line, MTM and ARTC are operated or managed. And V-Line, MTM and ARTC may not be knowing how Vic Roads are operating. Except there are situations where we are giving advance warning signs. That means we are giving advance warning that a rail is a train is approaching and vice versa. Now, how do we mitigate this high risk and all? The operational limitations for a train, you see. When a road vehicle enters a level crossing in the path of the train, the only action what a train driver can take is by sounding the horn, or if this vehicle enters suddenly, all what he can do is simply apply emergency brakes. And when he applies emergency brakes, he requires quite a distance to come to a stop. So that is the limitation. See, he may or he may not be able to stop before he actually hits the vehicle. Or given the limitations of braking and accelerating trains, by necessity, motorists must give way to the trains at level crossings. While this may sound obvious, the actual data indicates that majority of the level crossing accidents are because of the motorist not abiding by this simple rule that they are supposed to give way to the trains. Okay, now coming to level crossings in Australia in particular. See, there are totally about 23,500 railway level crossings in Australia, and out of which 21% of level crossings in Australia are active. And I'll come to that, where you call it as active and where you call it as passive. That is, they have boom gates or flashing lights, and 79% are passive, where they don't have anything. They just have a stop sign. Okay. Now, the first question is, who is responsible for mitigating this high risk area? In Victoria, Victorian Railway Crossing Safety Strategy 2018 to 2027, that is one agency, and the second agency is National Rail Safety Regulator, who have a level crossings policy. Then how is this done? This is done by, there are three methods, which is applied. One is the Australian Level Crossing Assessment Model, ALCAM. They have reports, and they have statistics where whether the level crossing is supposed to be closed or whether it is to be upgraded or whether it has to be made from passive to active and all that. And then second thing is the Australian Transport Safety Bureau. That is another agency which decides what needs to be done with a particular level crossing. And then the ongoing projects, based on these two studies. And then what are the plans in progress and planned? See, in metropolitan Melbourne, under a massive level crossing removal program, 85 dangerous and congested level crossings are being completely removed by grade separation, along with other signaling upgrades. And many of these projects are already in progress or they are commissioned. And in regional Victoria, various level crossings are being upgraded to a higher level of protection under the Regional Rail Revival Program, which is upgrading every regional passenger rail line in Victoria. Now, just to give an idea, I'm going to tell you about what is which level crossing is considered as passive and which is considered as active. Passive level crossing control of the level crossing is movement of vehicular and pedestrian traffic across a level crossing by signs and devices only, none of which are activated during the approach or passage of a train, which rely on level crossing user detecting the approach or presence of a train by direct observation. That means only stop signs are there and the vehicular traffic needs to come and stop at the level crossing by following these type of signs, and then give way to the train, and once the train passes, then he is allowed to cross the. The controls may include stop and give way signs or pedestrian mazes as you see in this image here, or cattle grids or manually operated gates. This is passive control. And then active control is the control of the movement of vehicular and pedestrian traffic across a level crossing by devices such as level crossing warning lights, boom barriers, and audible warning devices like bells, or a combination of all these above, where the device is activated prior to or during the passage of a train through the level crossing. Types of crossings with active control are public level crossings, private or occupational level crossings, service or temporary level crossings, and pedestrian level crossings. Now, coming to the design aspect of the level crossing, a typical single line level crossing signal arrangement plan will be as I am showing it on my screen. So for this will have nowadays the type of level crossing activation. We are using axle counters. So we will have axle counter here, and then just across the level crossing we'll have two axle counters, and the other one at the far end, of the down direction. And if you want to let me describe, what these different things are. See, this is the warning time and the which is based on the line speed of the train, and these are flashing lights which are given for the road users, and then there is across the level crossing, which is there is a axle counter section or the track circuit, which is called as the island track, and then these are called marked with boom and flashing lights and bell, and HSK, that is the power supply indication. And then we have the approach tracks. This will be the down approach for the trains moving in this direction, and for train moving on towards Melbourne, you will have the up approach track. And the first axle counter, this is called as the striking point for the level crossing. That means once the train strikes this striking point, then the level crossing safety devices are activated and the level crossing starts closing. So now the design parameters which are used, see, the warning time, the minimum warning time, for which the standards have actually through experience and through different case studies and all, the minimum warning time what they have arrived at is 25 seconds. I'll tell you the details how it is arrived later on in another site. And this minimum warning time also depends upon the crossing width. That means the crossing width is not across the track, it is across the road. And the angle at which the road crosses the railway track. And then this warning time also depends upon the train detection, the type of train detection which is used. Nowadays, we are using more axle counters, but there are other types of train detection also which are used. And then the last thing, warning time depends upon the CBI technology, because different types of CBI technologies are used. For example, electrologics is used, then SSI is used, then microlock is used. So, and all these technologies, they have they differ, in their activation times. So that affects the warning time. And then the other design parameters are traffic light coordination. Suppose there is a traffic light signal which is leading into this level crossing, that also affects the design of the total level crossing system. And then, like I told you before, we give some advanced warning systems to the road users. So that also has some little some effect on the design of the level crossing system. And then naturally the line speed, the maximum and the minimum line speed at which the trains are actually crossing the level crossing, that also has that is also one of the parameters. And then the island track, which is usually 40 meters, but now the standards have actually mandatory requirement they have made that all island tracks have to be minimum 40 meters length. And the other things are whether the level crossing is a standalone level crossing or it is an interlock level crossing. That means interlock means whether the level crossing is interlocked with signals or whether the level crossing is present in interlocked areas or yards. And then another parameter which actually affects the total design is whether what type of trains are passing through the level crossing, whether they are all express trains or whether they are all stopping trains, and whether there is a platform at the approach of the level crossing. That also has got a effect on the total design. And lastly, but not the least, whether the lines are single line or they are double line. So because if it is a double line, like what I am showing you in the sketch here, then the approaches to the level crossing will be different for the different line, because one line will be down line, which will be having only down approach, and the other will be up line, which will be having only up approach. And here, see, we are currently whatever type of detection and control is being used, I have shown in this slide. The train detection, we are using axle counters maximum, and then we can also use conventional track circuits like HVI track circuits or DC track circuits. And then we can also use predictor systems like GCP 4000 and HXP3. They are predictive systems. That means they detect the motion of the approaching train and accordingly decide on the distance, the approach distance, and then calculate and then transmit to the interlocking how far is the train and how the level crossing is controlled. And we also use CBI, different CBI technologies, or maybe relay interlocking. And that is, electrologics we are using, microlock we are using, SSI we are using, like what I told before. And there are some places where it is mixed. That means in the down direction, it may be electrologics or microlock, and in the up direction, it may be relay interlocking or maybe SSI. Now I go to the actual operation of the gate, and then here I will tell you about how we come to that the 25 seconds time, minimum warning time. First, there are different stages, stage A, stage B, stage C, and then finally stage D. And then if there is traffic light control, then you have stage H, you have stage E, you have stage J, and all that. So the first stage will be stage A. That is, once the train strikes the striking point, the flashing light and the bell are activated. That is called as the stage A. And this stage A continues for 7 seconds. And then if the level crossing is having boom barriers also, then the boom barriers commence to lower. That is called stage B. And between stage A and stage B, you have 7 seconds. 7 seconds, the flashing light and bell will continue to operate. And then after 7 seconds, the boom barriers start lowering. These boom barriers, they start lowering and they come to the horizontal position roughly within 12 seconds. So once the 12 seconds time has elapsed, the boom barriers will be horizontal, and that will be stage C. Okay, so totally it comes to 19 seconds. And then finally we give some relaxation for the booms to completely come under horizontal position. So we are giving about 6 seconds allowance. So 7 plus 12 plus 6, this comes to 25 seconds. And now the last stage, that is stage D. The stage D is there only in the case of successive operations, successive trains, which are striking the level crossing. For example, I'll tell you. Suppose one train has strike the striking point, and it is going in the down direction, and it is just reached the island track of the level crossing, and it has not crossed the island track, but it has just reached the island track. And at that time, suppose now the train has just crossed the island track. That means the booms will start to open. At that time, suppose there is another train which is striking the striking point. So suppose the boom is just getting it is opening. So suppose the next train strikes the striking point. That means the boom should again lower and close. So to avoid that successive the booms closing for successive operation, the stage D is introduced into the operation. That is, between two opening and closing operations, minimum 25 seconds duration is ensured. That is called as stage D. So for successive operation of two trains following each other at close proximity, once the onward advanced train crosses the island track and the boom starts opening, then it will open and it will keep in the open position for 25 seconds, and then only it will start closing for the next train. So these are the different stages of operation for a level crossing. And then coming to the traffic light coordination. See, when a traffic light signal is in close proximity to a level crossing or leading into a level crossing, we have something which is called as a traffic light coordination. The safety system at the level crossing is coordinated with the traffic light coordination, and where a road intersections with the traffic lights and pedestrian road crossings occur near a railway crossing, the traffic lights are coordinated with the level crossing. This is to prevent a conflict between the display of the traffic lights and the flashing lights at the level crossing. The traffic lights should not display green, leading directly into a red flashing lights. So if that happens, what happens is the traffic will get accumulated at the level crossing, and it may block the traffic at the junction where the traffic light is there. The control systems of the railway crossing protection and the roadway traffic lights are interconnected by a 20-pair communication cable, and information is passed between the two systems in a standard format defined by the WIC roads. Thin information enables the two systems to provide coordinated information to road users. The level crossing protection system advises the road traffic controller of the approach of a train before the level crossing protection is activated. That means, like in the previous slides, I showed you that there is a control track, down control and up control. And in addition to this down control and up control, we have something which is called as a down holding and up holding track, which is minimum of 25 seconds is given for that holding track, and maximum we go up to 35 seconds. So that is what he means by the level crossing protection system advises the road traffic controller of the approach of a train before the level crossing protection is activated. That means once a train strikes the holding section, the traffic light holding section, the information is sent to the traffic light coordinate control box by a call or relay. This call or relay picks up when the train hits the holding section, and that information is conveyed to the traffic controller box through this 20-pair communication cable, and at that time what happens is the road traffic lights will transition into a train phase in an orderly manner prior to the operation of the level crossing protections. Generally, road traffic lights coordinated with level crossing protection provide a clearance phase in between, that is just before the train phase, to enable the road vehicles to exit from the level crossing while preventing additional vehicles from entering the crossing. That means the traffic lights will go into red. Immediately the call or information is given to the traffic light control box, and there will be a clearance phase in between, so that the road vehicles which have already crossed the traffic light, they can clear the level crossing. And once the clearance phase is over, then what happens is there is a response given to the train interlocking through a TLR relay, traffic light response. That TLR relay picks up, and then the level crossing protection will start getting activated. Usually the call to the traffic lights is provided by the holding section of the level crossing, 35 seconds being sufficient in all cases. In some cases, less time is necessary for the call section depending on the road, if the road intersection is simple with limited cycles. That means if there are only 4 roads in the traffic light, then 35 seconds is considered as sufficient, and or they even give minimum 25 seconds are enough for the traffic light coordination system to work properly and safely. So now I come to something which is called as express and stopping controls. That means if a mixture of trains, if type of trains are going in the tracks which are passing through the level crossing, and suppose there is a platform which is just next to the level crossing, and trains normally stop at that platform and then go, and there are some trains which are express and which don't stop at the platform. So then what happens is we give separate control sections. We give a stopping control, and then we give an express control. And express control will be minimum warning will be just like what I told before, 25 seconds at line speed, and the stopper control will be typically between between 50 to 55 seconds, which will consist of 20 seconds for the train to come at a halt on the platform, and roughly 20 seconds dwell time at the station is given because for the passengers to get down and alight the train, and then 10 to 15 seconds to move from rest until the front of the train enters the crossing. And this particular stopping control and express control, they are controlled by a signal which is at the end of the platform. This signal will be at stop for the stopping train, and if it is an express train, there is a system through which we call it as pre-clearing of the signal. So for an express train, this signal will be pre-cleared, and as the train approaches this signal, the signal will clear, and the train can go at line speed and pass through the level crossing. So that comes to the end of my presentation, and I'm open to questions now.
Thank you so much, Sheshadri. Just one question on the intermediate time you said about that between a closure of the level crossing and then opening it again. I think it should be 15 seconds, not 25 seconds.
No. Section stage D is 25 seconds in Victoria. Maybe less in some other areas, but for in Victoria we always give 25 seconds time.
Okay, right. Thank you. Because in most of the ARTC designs, what we are following 15 seconds in Victoria.
Yeah, maybe. Yeah.
Oh, right. Thank you.
Yeah, good evening, sir. Sheshadri.
Haji.
Recognize me? Okay, Jain?
Sorry, I'm not able to make out.
You met
Ah.
in one.
Tell me.
So regarding level crossing timings,
Yeah.
this is standard or something is varied from section to section, and
Yeah, it varies. It varies from section to section, and it also depends upon the crossing width. For example, if the crossing width is say 10 meters, then 25 seconds is considered to be optimum, and for every meter more than 10 meters, we are increasing by 0.35 seconds. So before our design starts, generally what we do is the crossing width across the road is measured, and for every meter more than 10 meters, we increase the warning time.
okay, thanks.
And if it is a pedestrian crossing, the same thing is 1.35 seconds for every meter increase, more than 10 meters.
Okay. Basically, we are considering this pedestrians average pedestrian speed, how we can pass that.
Sorry?
If we are considering how the average number of pedestrians will pass the crossing at the speed means very quickly, pass very quickly, some may cross very slowly. Also, we have taken as the average standard.
Yeah. That's correct.
Yeah, thanks.
Yeah.
Good evening, Somnath sir and Sheshadri. Sir, I work with, I am Ranjan Gaukar. I worked with you for little time while in MCML.
Oh, okay.
Very good.
Is there any possibility there can be some session on GCP 4,000?
Yeah, we'll try to do some session. Yeah.
Yeah.
We'll keep that in mind. Yeah.
Yeah, like something about how to decide the frequencies and some part of programming of it.
Yeah, that's a good subject. We'll try to do it. Yeah.
Yeah.
We'll take care of it. Yes.
If it is, yeah, we will like to actually join if sometime it takes place.
Yeah, we'll note it. Yeah.
Okay. So if there are no more questions, shall we proceed to close this session?
Yeah, I think so.
Yeah. So thank you, Seshadri ji, for telling us about these level crossing controls in the Victoria. I think it was quite enlightening, and we had a lot to learn from it. And the presentation was very clear. What you made was very clear to us, and thank you for that, for the presentation, quality of the presentation.
My pleasure, sir.
And thank you today for those who have been present in this session. And we have recorded this, as I mentioned in the beginning, and will be put on the YouTube shortly after I finish the. You need to do some finishing before it goes on the YouTube. I know there are a lot of visitors to those videos that I put in. It is it's helpful to all those in future as well, that there are many earlier videos which are there. So any of you can go to the to our link. I have a website link to the YouTube, so everybody can see that at their own time. All right. Thank you very much for joining this session, and we will, with this, close our session today. Thank you.
Yeah, thank you.
Bye.
Thank you so much.
Bye-bye. Bye.
Thank you. Very interesting session. Thanks to both of the speakers.